presenting virtually from Sicily, where it's late at night or early in the morning.
Good afternoon. Yeah, this is late night. This is the 28th. My name is Antonio Di Stefano. I'm the head of R&D of Prismian Electronics, and I will present my replication of the LEC, as well as many experiments and observations that I have done on the active device, as well as on the control device. I believe that it was important to test also a control device because there are some similarities with other technologies that employs bimetallic systems and gaseous electrodes and something like that. So I wanted to be sure that I was not observing some conventional phenomenon. And moreover, the signals that I was measuring was quite small. So I wanted to be sure that the measurement instruments were okay from the noise point of view, interference, electromagnetic interference point of view, and DC drift. So I built a device made to be modular and easy to assemble. It was composed by two coaxial tubes of few millimeters in diameter and 10 centimeter long, more or less smaller than a pencil. And the gap between the two tubes is 0.5 millimeter. And there are spacers made from silicon rubber to maintain this space. The inner tube is also used as a gas inlet and outlet. And I made 3 different outer electrodes, one of brass as the inner tube, one of copper and one of aluminum. This is to test the impact of different metals on the device performance. The dummy device, the control device, is different from the active device only for the lack of the electroplating on the inner electrode. So the tests that I made on the control device were quite extensive. I made tests with air and hydrogen at 2 different pressures, and using a quite sophisticated instrument that has a lot of options for attenuating or removing noise and filtering mains frequencies, for example. First test was on the open circuit voltage from the dummy device. This test resulted in essentially no voltage measured on the 3 metal pairs. Of course, in this condition, no current was present also. The second test was trying to measure the conductivity of the device, the capability of carrying current through the air gap. I applied a voltage from -60 to +60 and measuring the current. Also, in this case, essentially no current was measured. So this test was repeated for both gas and both pressure and all the 3 metal variation of the device. This allowed to make a robust conclusion, 2 robust conclusions actually. One is that the passive LEC device, the dummy device, the control device, is not able to generate a voltage in any of the tested condition. And also it is not able to conduct a current. Moreover, this test was very useful to assess the instrument sensitivity and noise level. The next step was to make the device active. This was done by taking the inner electrode and electroplating it. I've done this by using a diluted hydrochloric acid solution and some iron wires as anodes. I used quite small current density as suggested by Frank. that required a very low voltage, less than 0.5 volt usually. The process lasted for 8 hours. In the first 6 hours, essentially quite nothing happened except for hydrogen evolution at the cathode. Then the last 2 hours, the electrode became black. A thin layer of a black coating appeared. This layer was very thin, something like 10 microns or something like that. And it was not shiny at all, as expected from an iron plating. This is because probably it has a nanoporous structure. Also, strangely enough, the electrode became magnetized, very magnetized. This was probably because the formation of magnetite crystals on the process, as suggested by Alan Smith. Once I get this result, this electrode, I washed it and dry it very well and inserted in the outer tube, just in plain air, without adding hydrogen, expecting some difference from the control device. In fact, the behavior was very different. I measured the voltage, the open circuit voltage, and I found that it gradually increased up to about 300 millivolt, and the short circuit current was about 2.4 microamps. So the device was clearly generating some energy, some power. So very rapidly, I swapped the outer electrodes to see what would be the effect of changing the metal pairs. Essentially, the voltage and the current were the same order of magnitudes. The only notable things was that the aluminum electrode reversed the voltage, the polarity, either of the voltage and the current. From this very simple measure, we can observe 2 important things. One is that once you assemble the device, it took some 1 minute or so to stabilize the voltage. It increases slowly. This is because probably there is something that has to build up. And this is probably the ionization of the internal gas. This is also confirmed by the fact that the device is now relatively conductive. 2.5 microamps seems a very low quantity, but is more than 3 orders of magnitude greater than the control device. We will return on the aluminum polarity inversion later. The subsequent experiment was to measure the capability of sustaining an electrical load, a resistive load. I changed the resistor attached in parallel to the device from 10 mega ohm to 1 kilo ohm, the same experiment made by Frank. And I obtained this plot that you can see on the left, that is exactly the same that Frank presented. And from this plot, you can see that the maximum power transfer is obtained at about 120 kilo ohm. That is also the resistance of the internal generator. The other test was even more insightful. I tried to measure the forced current of the device, applying a voltage, external voltage from minus 10 volt to plus 10 volt. And I obtained this curve that is very meaningful in that it is pretty symmetric. This means that the charge generation is quite symmetric, and the presence of the charge are both positive and negative in an equal measure. This is symptomatic of an actual gas ionization. And also you can see that there is a slight saturation at the extremities. This is also indicative of a gas saturation where all the available charge carriers are used for the current. This is something similar that happened on thermionic diodes, for example. Both these facts suggest that the gas inside the device is actually ionized. The next test I made was to try to store the energy produced by the device. I connected repeatedly a 100 microfarad capacitance and collected the energy. Each charge of the capacitance accumulated 4.7 microjoule of energy. From the time constant of the charging, you can calculate that the internal resistance is the same order of magnitude of the one that we calculated before. This energy may seem a very small quantity, but it is sufficient to run some modern electronic circuit, CMOS circuit, for example. And you can collect a lot of this energy from the device. So it was quite clear that the device was capable of ionizing the gas inside it. So I tried to measure also the radiation emitted by the working electrode. I used an alpha-sensitive Geiger tube, and I tried to set close to the working electrode, but apparently no radiation was measured in an integration time of 5 minutes. This is quite puzzling. Some reason may be that the radiation is not the same type that we are used to measure, not alpha, beta, or gamma, or the energy of the radiation is quite low, let's say less than 1 kilo electron volt. This cannot be detected by the Geiger-Müller tube. Another option, another hypothesis that is partially confirmed by other evidence is that the emission is not uniform over the surface, but it's from few hotspots. So you can measure it only if you find this hotspot and place the detector on it. As an additional measure, I try to verify if the working electrode emitted some extreme UV radiation. I used a couple of tape of, let's say, scintillator, but I was not able to detect any fluorescence by naked eyes also. I didn't use a photomultiplier, however. So let's come back to the question of the polarity inversion for the aluminum electrode. In order to investigate this result, I tried to replicate the bimetallic system with a liquid solution of 5% sodium chloride that has a same amount of positive and negative ions, and obtaining quite the same voltage levels, and also the polarity reversal for aluminum. This is clearly due to the electrode potential or work function of the two metals. This suggests that the voltage generation inside the device is a secondary effect due to the interaction of the ions with the metals, and the primary effect is the ionization itself. So I suggest to use the current as a means for characterizing the device more than the voltage, because the voltage is affected by the variation of the work function with temperature and other parameters. As a practical consideration, my device made with iron had a very short duration, something like 1 day in air or a few days with hydrogen, because the surface oxidized at a very fast rate. So from a an engineering point of view, it's not the best solution, maybe need to be improved, even if it is very simple, easy, and low cost. About the fact that the plating, the co-deposition step is something important for the working of the device, I tried also to use iron electrode and just electrolytically loading hydrogen in it. This showed no effect at all. So the co-deposition step is an important step and is necessary for the working of the device. So in conclusion, the behavior of the LEC device cannot be explained with conventional effect, and it's probably something new that needs to be investigated. Nevertheless, the replicability of this device is very high, and it does not require very pure elements to be built. I used even tap water and, as Frank said, the household equipment, more or less, to realize it. The electrical measurements suggest that the gas is ionized. And this is very interesting because in order to ionize air, you need energy in the order of or greater 10 to 20 electron volt that are 1 order of magnitude greater than typical chemical energy. As I showed, the voltage probably is a second order effect, the voltage generation. The prime effect is the ionization of the gas. So in order to characterize the device, to investigate how to increase its performance, it is better to monitor the current and not the voltage. And finally, the radiation that probably ionized the gas was not detected, so need further investigation in order to understand what is it, essentially. Finally, a couple of practical considerations. The power output of the device is relatively small, but in the practical region, it is similar to the power provided by some beta-voltaic batteries, but without any radioactive element. And also the most important thing is that even if we didn't understand how it works in details, there are many possible ways to scale up the energy and power output of the device. For example, by multiplying the surface or something like that. So this concludes my presentation. Thank you for your attention.